Hello and welcome to a video on Class AB amplifiers. So in this video we're going to look at the principle, what a Class AB amplifier works against, then the BJT Class AB and the MOSFET Class AB. So each has some ways to make this happen. We have a diode bias for BJT, VBE multiplier, which is an interesting trick to learn. Then for the MOSFET, we can do it with resistors, and we can also do it with diode connected MOSFETs as well. Okay, on to how this works. So previously we looked at a Class A amplifier and a Class B amplifier. Now the Class A amplifier has output offsets, or you need to provide an input offset to make it work. It is very inefficient, 25% efficiency. There is, however, no crossover distortions, and it requires a bias. A Class B amplifier doesn't require any biasing. It has crossover distortion because these transistors are not switched on. It is very efficient, and it has no offsets because it's balanced. So the Class AB amplifier is basically a cross between the Class A and the Class B amplifier. So if we look at the sketch here, we can immediately see the Class B amplifier, and what we have done is add some biasing element here to it. So basically you switch on these two transistors at a very low current beforehand, and that eliminates the crossover distortion. So we give it a small VBB value, small bias voltage, and a quiescent current will start to flow through these two transistors, which is approximately the same, assuming we have large beta values. And the voltage required here at the input is VBE1 plus VBE2. Right. Another thing that's not showed here is that you also need to require the base current for the transistors for it to switch on. So the negative effects is you will lose a little bit of the efficiency that you have, but the positive side is there will be no crossover distortion. But applying this bias makes it a little bit more complex. So the first way to create a Class AB amplifier is by applying two diodes here on the base of the transistors to bias them. Okay, so the current flowing in the first diode is the same as the current flowing in the second diode, and this will create our VBB value. Right, so VBB is the same as our two diode voltages, and it's the same as our two VBE and VEB values right here. So the first observation is that we create the voltage with the diodes. Then if we have matching diodes, these two will obviously be the same, the two voltages, because there is the same current flowing through them. The second observation we can make is that we need to supply current to switch these diodes on, and we need to supply current to switch this transistor on. So I bias would be the current to create the specific VBB voltage, and the maximum amount of current required when this transistor is switched on and driving a load. Right, so our voltages need to be very, very precise when biasing these transistors. We can't just apply voltage here. We will switch these transistors on at a very high current, and it will be pointless because we will have great losses or too much current flowing in these transistors, burning them, or in general, it would be bad. So we need to precisely calculate the diode voltages and our transistor on voltages right here for a specific current. Okay, so for a diode, it is IS, the saturation current, E to the VD over N times VT minus 1. Okay, in general, this is much larger than 1, so that's where the approximation comes from. Always remember that a diode will have this little N included in the equation. If you forget that, these problems can mess you around for quite some time. So, this N in books is typically assumed to be 1. The value is in general between 1 and 2. Okay, so this you will find in the SPICE model of your diode. So you need to calculate the diode on voltages for a specific current flowing through them. So you can calculate the current that you want or need to flow for a specific VD. And you can do the same for the transistors. IC is ISE to the VBE over VT right here, or rewritten in the format VBE is VT ln IQ over IS. So you design for a specific quiescent current. So the saturation current right here you will find in the SPICE model. And you need to calculate that independently for each transistor. Unless if it is matched transistors, then this IS will be the same. So typically you try and match your components in any case. Okay, so on to a little bit of a design. Let's say we want a quiescent current of 1 milliampere flowing, and we are going to drive a load of 100 ohms. VCC and VE is 10 volts plus minus 10. And now it becomes important to know which components we are using. So I've chosen the 1N4148 diodes, and their saturation current is 5.52 nanoamps, and N is 1.752. Then for transistors, I've chosen the quad 2. So it has a 10 to the minus 14 ampere saturation, and the 2N2907 has the same saturation current. Okay, it's also important to know the beta value of this NPN transistor right here. Okay, so with this we have everything to design our class AB amplifier with a diode bias. Okay, so the bias current required up here is what we need to flow in the diodes and what we need to flow into this transistor. So IB1 maximum would be VCC over R load. It's 100 milliamperes to drive this load, divided by our beta value is 500 microamps. So we need 500 microamps to drive that transistor. Great, so that is the first current calculated. Next, we need to find the voltage required to switch on these two transistors at a quiescent current of 1 milliamp. So VT ln IQ over ISN plus VT ln IQ over ISP. Since they are the same, these two values will be the same, but that boils down to 1.266 volts. Okay, so over each diode we require 0.633 volts. So with that we can calculate the diode current required, and that is 4.763 milliamps. And if we add it right here, we get approximately 5.3 milliamps as our bias right here. Okay, so we're first going to have a look at all the diode bias configurations, and then we're going to do some simulations, and then move on to the VB multiplier. Okay, so in all our problems, we are going to use the same components. So the bias current required here, 5.3 milliamps, will be the same in all our following problems. And our VBB as 1.266 volts right here will also carry over through all our problems. Right, so this is how to calculate the current required to flow in these diodes. Now, if you have that, we need some way to build a current source up here. So there is a couple of ways to do this. In these problems, typically this one we see this Vin as a ground point, because this current will flow in there and this current will also flow that way towards a ground where our input is. Okay, but we don't always want this to happen. So there is a couple of configurations for our diode bias. So the first one is how to create our current source and have it nicely balanced like this. Okay, so we need a bias current of 5.3 milliamps. So we will have 5.3 milliamps flowing in this resistor up here. Roughly the same amount of current will flow in the resistor down there. And right here in the middle, we have our VBB value at 1.266 volts. So we can just apply Kirchhoff and say that VCC is I reference or I bias times R1 plus VBB plus I reference or I bias times R2. So nice Kirchhoff's law. Calculate the two resistors combination, 3.53 kilo ohms. If we assume they are the same, 1.66 kilo ohms, 1.8 is the closest E12, and that is the design for our resistors. Okay, so if you include the inputs like this with two capacitors, there is no current flowing into the circuit before here, and nothing can influence the bias of our circuit right here as well. And we can get plus minus 9.7 volts output right here with no offset, so no output capacitor required here. Right, and that is doing the bias with resistors. Then the current source. So assumption is this point is a ground. Now this circuit here in the corner is the most basic current source that you get. Note, this transistor Q4 is diode connected. So the current flowing into it right here and out of it on this side is the same. And applying Kirchhoff, we have VEB plus I reference times R reference. So that creates a nice reference for us. Now, the VBE here and the VBE here would be exactly the same. So if they are the same, it means that the current in the reference is duplicated here for the bias. Okay, so if our reference current is 5.3 milliamperes, our bias current would be roughly 5.3 milliamperes. So this is called a current mirror. So what it sees on this side will be mirrored over to that side. Right, so we assume that our VBE, or sorry, our VEB value for here is 0.7 volts. And we can calculate our reference resistor. So 10 minus 0.7 over Iref gives us roughly 1.8 kilo ohms for the reference resistor to create a 5.3 milliampere current to flow here, and it will be duplicated on this side. Right, most of these circuits where we assume this is a ground at our input and whatnot, and all these currents are flowing out of here into the previous circuits, will have output offsets. A rail to rail operation will be difficult, and you probably need to remove output offset with a capacitor right there. Okay, so in general, this is not a very good configuration to use. Crude, but there is better ways to do this. Okay, so this circuit right here is pretty much the same as the previous one. We just have two current mirrors. So VEB here and VBE right here, we assume them to be mirroring the current on both sides. So it's the same as what we had with the two resistors. So the current up here and the current down here is the same, and the current flowing in this reference resistor is the same as those two currents, and it creates or causes this circuit to be nicely balanced. Okay, but this is a very complex kind of setup. So the assumption is that this voltage and this voltage is 0.7. We'll mirror the current over to that side. So we have VCC is IREV, REV minus VEE, and subtract both these VBE voltages. And if we divide that by our reference current, we get 3.3 kilo ohms for our reference resistor right here. So these current sources are quite easy. It's just Kirchhoff from top to bottom and know that it will mirror whatever in these transistors right here. Okay, so you can include your input right here between the two diodes. Just note that you will lose 0.7 volts because of the diodes, and it requires matched devices. Okay, this is very important. Everything needs to be matched in this design for it to function properly, else you're going to sit with a lot of offsets here at the output. Okay, right, so note that there's no capacitor on the output, there's no capacitor on the input either. Okay, and that is it for the diode biases. Let's go and have a look at our simulations for these. It will be kind of quick. So our first one here is just our diodes and our current source. So I connected a ground here on the input. So we have 5.3 milliamperes flowing through these diodes, and almost nothing here on this side. If we have a look, 1.4 milliampere, we were designing for 1 milliampere. So having your stuff precise we'll have this closer to 1 milliampere in general. 1.4 is not so bad. So yeah, your component choices will have a huge influence for your biasing and the final result. So there is our output, there is our input, they are very close. Look at the offset that we have between from here to here. That is a bit of a problem. So if we were to make this 10, we will have our output clipping at the top right there. So let's see, 9.7. We still have clipping, so it's not the 0.3 of a rail. And I think 9.3 will be okay there. So plus minus 9.3 volts output. And that is due to our diodes right here. Okay, and that is our current source one right here. Let's have a look at our next simulation. Our next simulation is our resistor biasing. So if we run this, we have 5.3 milliamps flowing up here and down here. There's a little bit less going on in the diodes because that is what's going into the transistors. Top current, bottom current, final voltage. Note that this is very close to rail output. 10 volts in, plus minus 10 volts out. So yeah, that is the resistor bias. Quite easy. Let's move on to our current sources. So here we have our current sources. I just use the same PNPs as what we had already. You don't have to use the same transistors because these are power transistors. You don't want to duplicate them. It will be quite expensive. You can use other transistors here since I won't be pulling a lot of current. I just did this for simplicity. So if you run this, you have a little bit more than 5.3 milliamperes being supplied into these diodes. Okay, see these two are quite close to one another. And if we would run this, there is our output. And from our input to our output, there is some offsets. So this will again be 9.3 volts. And then it clips. So using an unbalanced current source like this is typically not a very good solution. You must rather have it balanced. So not even close. Rail to rail, not possible at all using this configuration. But using a current source like this is quite simple. I would rather go for the resistor bias personally. Onto our next configuration. Right, our next configuration here is the one with the diodes in the middle, but it doesn't require any capacitor. So there's our input, and there is our output without any offsets. But only 9.3 is possible right here. And that is our diode bias circuits. So on to the VBE multiplier. The VBE multiplier is a circuit that we are going to use to replace our two diodes right here. So we can use the transistor in the same way. So we are going to require a current source again. And this current source, as usual, needs to supply our transistor and it needs to supply the VBE multiplier. Okay, so I bias is IB1 maximum plus the current flowing through the resistor plus the collector current of this transistor right here. And we assume that, or if we make the choice, our current flowing through this resistor must be much greater than our base current flowing right here, so that we don't need to worry about the base current. And with that, if we don't need to worry about the base current, VBE of this transistor is equal to IR1 right here. Okay, so that is our regulator component right there, is the current that we choose and the VBE voltage of this transistor over R1. Right. Now VBB would then be the current flowing through these resistors times the two resistors themselves. Okay, so these two are our design equations. Again, we need to calculate our VBB value from our two transistors, and we must also, with our collector current choice here, calculate the VBE value of this transistor that we use right here. Right, so the best to go through this is to do a design. So again, let's design for a quiescent of 1 milliampere. That means that this VBE for the same transistor is 1.266, like our previous problem, so we don't need to go through that rigmarole again. We require 500 microamps for this transistor. And let's say that we bias this transistor with 1 milliampere and we bias the resistors right here with 100 microamps. So if we are using the same transistor, the 2N222 like we had here, the VBE voltage of Q3 will be 0.633 volts. If it's a different transistor, it will obviously be a different value. Right. Now, with a current chosen for our resistors and a current chosen for our transistor right here, we already know what our bias current should be, and that is 1.6 milliamps. Okay, 0.5 plus 1 plus 0.1 right here. So that is easy for our bias. We can find a value for resistor 1. So VBE of 0.633 over 100 microamps is 6.33 kilo ohms, closest 6.8 kilo ohms. Then we can plug in the VBB value that we want and find our resistor 2 value. That is 5.86 kilo ohms, and let's choose that at 5.6 kilo ohms for our E12 value. Okay, and that is the design complete. Note with the choices of standard values here, our VBB value will be a bit off from this 1.266. So always check it in simulation, don't just build it. If these values are very far off, you can switch these transistors on at a too high current and cause some problems for yourself. Okay, so that is the basic VBE multiplier design. So we are going to use this R1 and R2 and VBB value and bias current throughout the next couple of slides. So the first way to do the current source is to do the resistor. R3 equals to R4. We have 1.6 milliamps flowing here, 1.6 milliamps flowing here. We know what our VBB voltage is, and we can calculate our two resistors using Kirchhoff's laws. So R3 plus R4 is VCC minus VEE minus VBB over our bias, and we get 11.71 kilo ohms, 5.85K, 5.6 kilo ohms for our bias resistor right here. Right, and that is the entire design complete. Okay, with our caps here on the input, no DC coming in, no DC leaving. We have no offsets on the output, and we can reach 9.7 volt output or very close to the rail for this configuration. The next one would be to use a current source. So again, we will have offsets, we can't reach the rails, and we need a capacitor on the output side. The only thing we need to design here is our current source. So the current flowing here is the same on this side, so 1.6 milliamps. So 10 minus 0.7 divided by 1.6 milli give us 5.81 kilo ohms, closest 5.6 Ks, like that. So designing a current source like this is quite simple. Okay, we are however neglecting any base currents in these problems. So we're assuming beta is quite large for our transistors we're using right here. Okay, the last VBE multiplier configuration is our balanced current source. We have capacitors on the inputs, and this can definitely reach rail to rail. It's not as bad as the diode voltage loss that we had with the diode bias. So again, just two current sources, so VCC minus VEE and 2 times a transistor on voltage divided by our reference current will give us our reference resistor right here, and that calculates at 12 kilo ohms. Right, this is a very complex design. The simplest is just using 2 resistors like we have here, rather than the current source like this. Okay, so if you're on the internet searching for output stages, you will find many flavors of class AB amplifiers. Okay, that's why I'm just showing a couple, and I'm sure it will be easy to figure out the mathematics, because this is probably the most complex that you'll get for it. Anyways, let's look at some simulations for these. So our first VBE multiplier connected the input to ground. We run it. We have our 100 microamperes flowing. This won't be 1 milli at this point. The 500 micro from this side is flowing through this transistor right here. So it is a bit self-regulating. And we have 0.4 milliamperes flowing in this transistor right here. Okay, this is not 1 milli because of our component choices that we had. So we check here, we have 1.255 volts. So 6.8 Ks, that takes us to 1.3, so that will move upwards again. So this resistor right here is very sensitive, and you'll find that this is sometimes just a variable resistor, so that you can tune your quiescent current to whatever you want it to be. Right, let's check this with our input connected. You see here we have a bit of offset. There's our input, there's our offset, and we need to remove the offset right there. I think this can go 9.3 without clipping. Let's check 9.7. But I think it will clip with 9.7. Yes, it clips with 9.7. Okay, so 9.3 is our output that we can achieve. Let's move on to our resistor configuration. So our resistors, 5.6 and 5.6. If we run this, we have roughly 1.6 going through both of these. We have no offsets, and we have almost rail-to-rail output with this configuration. Okay, so this is probably the easiest and best way to build a VBE multiplier class AB amplifier. Let's have a look at our other configurations. So here we have our current sources. So just a bit above 1.6 here. And there is 100 micro flowing through this side. 1.5 flowing through this side because there's not much going on this side. Yes. So 0.6 roughly. We add input. Note that we have offsets, and this one will be like the previous one. We're going to struggle to get anything close to the rail in any case unless we have a balanced circuit. So let's go and have a look at the balanced current source design. Okay, so here is our balanced current source. We run this. We have our 1.6 milliamperes flowing in here. Roughly 1.6 in here, but it spikes a little bit when driving the transistors. And we almost have rail-to-rail output right here. So this should be 9.7, then we won't have any clipping here at the top. Great. And that is our balanced current source design right there. No offsets at the output, but we require capacitors on the input. This is a very complex over design. Just go with the resistors. It will be the simplest, but you will find designs like this out there. So yeah, that is the VBE multiplier. Let's go and have a look at our MOSFETs. Right, for class AB for our MOSFETs, we need to give a bias, let's call it VGG, over 2, just like we did for the BJTs. Okay, so the quiescent current here is the same as our drain currents. So ID1 is ID2 is our quiescent. Our VGG is our VGS plus our VSG for our two MOSFETs. Okay, the nice thing for MOSFETs is we only require a base voltage, or a gate voltage rather. Sorry, that must be gate. We will have a decrease in our efficiency, but it will remove crossover distortion when biasing our transistors first. So, the first would be to build a plain resistor bias. So, doing Kirchhoff here at the back, VDD is the sum of these three resistors times the current flowing through them minus our VSS value right there. So the current flowing through these is a current of your choice. Typically as small as possible, so the resistors is as large as possible, so that we have a large input impedance like that. R1 will be equal to R3. No, sorry, R2. R2 will be equal to R3. There, fixed. Sorry about that. So this top resistor and bottom resistor will be the same. R1 right here will be responsible for our VGG value. Okay, so to get our VGG value, we need to find the voltage required for each transistor at our quiescent current. So if we choose 1 milliampere on this side, we're going to have to plug it into these two equations and find our VGS and our VSG value for our VGG. So if we put this in a problem, let's say we have two almost matching MOSFETs with a VTN of 1.1 and minus 1.1 volts, Kn of 62 amps and 22 amps. And if we calculate the VGSs at 1 milliampere, 10 milliamperes, quiescent current should be 10 milliampere design, which is more accurate. You usually design for 10% of your load current. You will find this at 1.12 and 1.13 volts respectively, and adding those two will give you 2.25 volts for our VGG value. And then you need to pick a current for these resistors. For this problem, let's assume it's 5 microamperes, and we get to 450 kilo ohms. Now, this resistor is best to choose the value downwards. The upwards choice will ensure that there is too much current flowing in these two transistors, and it will bring down your efficiency and your quiescent power dissipation in these transistors will be much higher. Okay, so rather choose it downwards. And if you have resistor 1, you can calculate resistor 2 and resistor 3, and this is at 1.8 mega ohms. Okay, I will show you what I mean with this in the simulation. Okay, so that is all we have on resistor biasing. So let's go to the simulation. Okay, this is by far the easiest way to bias our MOSFETs, but in any case, We have our 5 microamperes flowing. We have rail to rail output. And our VBB value, TGG value right here will increase if we choose that resistor upwards. Okay, let's remove inputs here quickly. $178 milliamperes with us at 470 kilo ohms, which was closer to the 450 that we calculated. Okay, 390. That is closer to the 10 that we calculated. Right, so it's better to choose that resistor downwards. Okay, and that is it for the MOSFET bias with resistors. The next popular method for MOSFETs is to use two diode connected MOSFETs here at the back. Okay, so if we put a current source right here, the current flowing through these two MOSFETs will create our VGG value right there. Okay, so if we match this and that device and this and that device, the VGS and VSG values will work out on the same voltages. Okay, so if you match the devices, it is quite easy to design this, but if you choose different MOSFETs here at the back, you need to recalculate the VGS values and VSG to be the same as what you had for the output devices for these, and find a new bias current. Right, so it can become a bit more complicated if you use different MOSFETs here at the back. Okay, and in that case, your I bias and your IQ will not be the same. But if you use matched devices, IQ and I bias will be exactly the same, and it will be a current mirror. Okay, so only thing that you need to supply here for the bias is 10 milliamps, and you will have 10 milliamps flowing on the other side as well. Okay, so you can bias this using one resistor, assuming that this is a ground point. And then we have VDD minus VGG is I bias R1. And you can calculate R1's value. Okay, so 775 ohms, 820 ohms, E12. Plain and simple. So it's just this voltage minus your VGG voltage right here, divide by the current flowing in it, and you're finished. Problem is, this will have offsets. So the best way is to do it kind of balanced and have resistor 1 and resistor 2. They will be the same value, and you will find using Kirchhoff that R1 and R2 works out at 820 ohms again. This is a slightly higher value than in the previous problem. So yeah, that is how you do the design using diode connected MOSFETs. This will be the best way to go, is using MOSFETs to bias our MOSFETs. This or our resistor connection right here. This one is easy to implement on a circuit board. This one will be easier to implement in a IC design, well, except for the capacitor right there. Yeah, before we go to the simulations, advantages and disadvantages of our circuits. Our class AB is efficient, but it's somewhere between the class A and the class B. So it's not as efficient as the class B, it's not as inefficient as the class A. Rail to rail is very possible with our MOS, 9.7 with our BJT. You can have no offsets depending on the configuration that you're using, and there is no crossover distortion. The disadvantage is the design is a little bit more complex than the class A or just the class B amplifier. Okay, let's go and have a look at our simulations for our diode connected MOSFETs. First up is our current source design. So I've grounded the input and we have 10 milliamperes flowing everywhere in this circuit on both sides. So this is kind of one of the nice things of the MOSFETs is current source design is quite easy. Yeah, anyways, moving on, applying the input. We have a huge offset in this circuit, so we need the capacitor on the output. You can probably push this a little bit more than you could have pushed a BJT circuit before it starts clipping. And there we go. So this is roughly at, what's that, 9.5 volts. Yeah, less. Okay, let's just go with 9. Okay, so due to this configuration being unbalanced, you will have offsets and can't have rail to rail output. So the final design that we had with the 2 resistors, if we run this, this is sitting roughly on 10 milliamperes top and bottom, and we have rail to rail output. It's as simple as that. So this is one of the best designs that we can have for a MOSFET. Right, we can also remove our capacitors and actually apply the input right there in between, and we can have output without offsets, so no capacitors in and out, but we sacrifice some of our rail voltages right there. So yeah, so there is another configuration. So you will find many flavors of these inputs at different places, sometimes with capacitors, sometimes without capacitors like this. Just when moving this around, you sometimes sacrifice some of your output rails. Any case, that is it for class AB amplifiers. See you in a next video.